Hello students. Till yesterday's class I derived that torsion equation from the basic principles. As we know that torsion equation is T by J is equal to 2 by R is equal to G theta by L is the torsion equation, which is T is the capital T is the torque applied on a shaft, J is the polar moment of inertia, 2 shear stress acting on the surface of the shaft, R is the capital R is the radius of the shaft, G is a rigidity modulus, theta is the angle of twist in radians, and L is the length of the shaft, isn't it? This is the torsion equation. By using this equation, we can solve the problems in torsion chapter, in this chapter. To use this equation, we should follow these assumptions. Some assumptions are there. The material must be a homogeneous and isotropic. The twisting along the shaft is uniform. The shaft having uniform cross-section or uniform diameter. Cross-sections are plane before twist remains plane after twist, and all radius lines are straight before twist after remains straight after twist. These are the assumptions. And polar modulus torsional rigidity are the two definitions we studied in the last class. And we derived the equations for polar moment of inertia for solid and hollow shafts, and power equation, power developed by the power transmitted by the shaft, isn't it? Up to this we discussed in the last class. In today's class, some worked example. We should work. We will discuss about the examples, worked examples, problems by using the torsion equation. Okay. Let us go for the example 1. Determine the power transmitted by a solid shaft of 5 cm diameter while it is rotating at 120 rpm. Maximum permissible shear stress in the shaft is 80 kilonewtons per centimeter square. The given data is, we should find in this problem power transmitted by a solid shaft P. Diameter capital D is equal to 5 centimeters, that is 0.05 meters. While it is rotating at 120 rpm, capital N, it is a speed of the shaft 120 rpm, it is revolutions per minute. A maximum permissible stress means the stress at the surface of the shaft is 80 kilonewtons per centimeter square, or 80 into 10 to the power of 7 newtons per meter square. It is pascals. Okay. If you want to find the power, you should know the torque transmitted or torque applied on that shaft. So from the torsion equation, we know that T by J is equal to 2 by R. The first two parameters from the torsion equation, T by J equal to 2 by R. By using this relation, we can find the torque. Torque T equal to 2 by R into J. Where J is the polar moment of inertia, it is a solid shaft. Given shaft is a solid shaft. For the solid shaft, the formula for polar moment of inertia is pi d power 4 by 32. Pi d power 4 by 32. From this, d is the 0.05 meters. Then polar moment of inertia is 6.136 into 10 to the power of minus 7 meter power 4. This is the polar moment of inertia. And in equation R is there, this is the radius of the shaft. Your diameter is given. R is equal to d by 2, diameter by 2, then we'll get a 0.025 meters. Radius of the shaft is 0.025 meters. Then from this equation, T equal to 2. 2 is the shear stress, which is 80 into 10 to the power of 7 newtons per meter square, 80 into 10 to the power of 7 divided by R is the 0.025 into J value is polar moment of inertia is 6.136 into 10 to the power of minus 7. Upon calculation of torque, we will get the value is 19635.2 Newton meter. Torque will be torque SI units is Newton meter. Okay, force applied per unit or force applied through a distance. Force applied into radius of the shaft is the torque. After getting the torque, by using the power formula, we know that power formula is 2 pi nt by 60,000 kilowatts. So 2 pi into n is the 120 rpm, it is given in the problem, and torque is 19635.2 Newton meter divided by 60,000. Then we will get the power in kilowatts. It is 246.74 kilowatts is the power transmitted by that shaft when it is rotating 120 rpm. To develop the maximum shear stress in the shaft is 80 kilonewtons per centimeter square. Clear? This is the formula. By using the torsion equation, we can solve the problem. Let us go for the second problem, second example. Example 2 is that a solid shaft of 10 centimeter diameter. A solid shaft of 10 centimeter diameter transmitting 74 kilowatts of power at 150 rpm. Your power is given, P is given 74 kilowatts, and speed of the shaft is 150 rpm, and diameter of the shaft capital D is equal to 10 centimeter. It is 0.1 meter. SI units. Determine, first bit is torque, second bit is the maximum shear stress, and third bit is the angle of twist in the length of 1.5 meters. So length of the shaft is 1.5 meters. Through that length, what is the angle of twist? Theta value. Angle of twist is theta. And the fourth bit is the shear stress at radius 3 centimeters, a radius of 3 centimeters. The second bit is the maximum shear stress. Generally, this maximum shear stress is occurs at the surface of the shaft, and also find the shear stress at a radius of 3 centimeters from the center. Take G is equal to 80 GPa, 80 gigapascals. This is the problem. This is the sum given in the second example. So given data is diameter, power, speed is given, and the length of the shaft is 1.5 meters given in the third bit, and G is 80 GPa or 80 into 10 to the power of 9 newtons per meter square pascals. And small r, take it as small r at any radius r, 3 centimeters, 0.03 meters. You should find the torque, maximum shear stress at the surface, angle of twist, and shear stress at a radius of r to r. Clear, students? So by the given data, power is given. By using this power, we should find the torque first. So power formula 2 pi nt by 60,000. First bit is torque. From this formula, T is equal to 74, that is the power is 74 kilowatts. 2 pi n is the 150 rpm, T divided by 60,000. In this equation, T is the only unknown, torque is the only unknown. So T equal to 60,000 into 74 by 2 pi into 150. Then we will get the torque on the shaft is 4710.98 Newton meter, 4710.98 Newton meter. This is the torque applied on that shaft. Okay. Second bit is maximum shear stress. Maximum shear stress is represented by tau here. From the torsion equation, we know that T by J equal to 2 by R. First two parameters in the torsion equation, T by J equal to 2 by R. From this equation, we can find the maximum shear stress. Tau equal to, we can write that rearrange that formula, tau is equal to T by J into R. T by J into R. Or T by J into D by 2. R is the radius, diameter by 2. As we know that J is equal to polar moment of inertia is pi by 32 d power 4 for solid shaft. So pi by 32, 0.1 is the diameter, 0.1 whole power 4. The polar moment of inertia value is 9.817 into 10 to the power of minus 6 meter power 4. So upon substitution of this polar moment of inertia in shear stress equation, tau equal to torque is 4710.98. Just now we calculated that 4710.98 Newton meter divided by polar moment of inertia is 9.817 into 10 to the power of minus 6, and the radius is d by 2, diameter by 2, that is 0.1 by 2. So upon calculation of this equation or this value, 23.9 into 10 to the power of 6, 23.99 into 10 to the power of 6 newtons per meter square. We will get the shear stress value in newtons per meter square or pascals. If you convert it to the megapascals, 10 to the power of 6 is represented as mega, therefore tau is equal to 23.99 megapascals. This is the shear stress, maximum shear stress at the surface of the shaft. If you take the R radius at surface, then we will get the maximum shear stress. If you take this radius R somewhere else, then we will get the shear stress at that particular radius. Okay. Third bit is angle of twist theta. Angle of twist theta. Again, from the same torsion equation, g theta by L equal to tau by R. Last two parameters I am taking from the torsion equation. G theta by L equal to tau by R. And this theta is equal to, we can write it as tau L by GR. Tau L by GR is theta. So theta is equal to, tau is the shear stress, 23.99 into 10 to the power of 6. Just now we calculated in the earlier bit. Into length is 1.5 meters given in the problem. Divided by G is the 80 GPa, 80 into 10 to the power of 9 newtons per meter square, into R is the 0.05. R means d by 2, 0.1 by 2 is 0.05. Therefore, then we will get the angle of twist in radians. Theta is equal to 8.99 into 10 to the power of minus 3 radians. Okay, clear students? If you convert into degrees, how to convert into degrees this? How to convert? If it is in radians, if you want to convert into degrees, multiply this value by 180 and divide it by pi. Then we will get into degrees. So theta is equal to 8.99 into 10 to the power of minus 3 is the value, isn't it? It is in radians. If you convert into, if you want to convert into degrees, multiplied by 180 divided by pi, then we will get the angle of twist in degrees. That angle of twist is 0.515 degrees. Okay, if you take the length 1.5 meters, through that 1.5 meters length, the angle of twist of the shaft is 0.515 degrees. Next, shear stress at 3 centimeter radius, tau R. It is represented by tau R. R means at any radius R, that is any radius R 3 centimeters. At a 3 centimeter radius, what is the shear stress? As we know that shear stress is proportional to radius of shaft. Already we know this formula, tau R by R is equal to tau by R. This is shear stress at any radius R divided by radius small r is equal to maximum shear stress at the surface divided by maximum radius, that is the radius of the shaft, capital R. So from this, tau R is equal to tau by R into R. So shear stress is proportional to radius. If R is equal to 0, small r is equal to 0, then shear stress is 0. If small r is equal to capital R, therefore tau R becomes tau. The shear stress is maximum at small r is equal to capital R. From this equation, we can calculate the shear stress at any radius R. So tau R is equal to 23.99 into 10 to the power of 6 is maximum shear stress at the surface divided by the full radius of the shaft is 0.05 into, we are finding the shear stress at radius small r, that is 3 centimeter, 0.03 meters. Smaller value is 0.03 meters. Then we will get the shear stress at a 3 centimeter radius is 14.39 into 10 to the power of 6 newtons per meter square, or 2r is equal to 14.39 megapascals. This is the shear stress at a radius of 3 centimeters, and this is the maximum shear stress. 23.99 megapascals is the maximum shear stress at the surface. So if we want to draw the shear stress distribution for across the shaft, we will get this diagram. So first to draw the circle and draw the diameter. From it at surface, the maximum shear stress, the shear stress varies linearly across the radius, and shear stress is 0 at the center, and which is increases linearly towards the surface. So at the surface, the shear stress is 23.99 megapascals. This is the maximum shear stress, and 14.39 is at a radius of 3 centimeters. At a radius of 3 centimeters, the shear stress is 14.39. Let us take this as a radius 3 centimeters at particular point. At that particular 3 centimeter radius, the shear stress is 14.39. This is shear stress increases from center to surface. Surface shear stress is maximum 23.99 megapascals, and shear stress at center is 0. So shear stress varies linearly from center to surface. Similarly, if you draw the shear stress distribution on other side, we will get the same diagram. So shear stress is linearly varying, maximum at the surface and 0 at the center. Okay, students, this is the shear stress distribution diagram across the cross section of the shaft. Clear? So we found that shear stress at any radius r, and shear maximum shear stress, angle of twist in the shaft, and torque transmitted by the shaft by using the power. This is the second example. Third example is taken as homework. You should take this as homework because it is a very simple problem. By using the torsion equation, you can solve this problem. Example 3 is a steel shaft of 10 centimeter diameter, that is the diameter capital D is 10 centimeters, is subjected to a pure torsion and is 20 meters long. That is the length of the shaft is capital L is equal to 20 meters. It is driving at one end while the power is taken off at the other end. It is used for power transmission. If the angle of twist is 30 degrees, the angle of twist is 30 degrees. Then find the maximum shear stress, torque, and power transmitting at 120 RPM. That is capital N is 120 RPM. You should find the maximum shear stress, tau value, and torque, capital T value, power transmission, P, capital P value. So take G is equal to 88 meganewtons per centimeter square. Converted into 8. This converted into newtons per meter square. Okay, this is you should convert this diameter into meters, and then you should convert the angle of twist into radians, and then substitute in the torsion equation. We will get the tau, T, and P. If you want to find the P after getting the torque, you should use the 2 pi nt by 60,000 formula to get the power. Okay, these are the answers. Solve this third problem, third example, and compare your answer with the given answers. Okay, shall we go for this example 4? Okay, example 4 is a solid shaft. Again, a solid shaft is required to transmit 96 kilowatts of power at 180 RPM. Power and speed of this shaft is given. Find the diameter required if the permissible stress is 60 megapascals. Find the diameter. What is the diameter capital D required if the permissible stress? Permissible stress means that is the maximum stress that can be allowed by the shaft. Up to that, the shaft can allow is 60 megapascal. That is the maximum shear stress. 60 megapascals, toe equal to 60 megapascals. Here maximum antunnanu, the maximum shear stress developed at the surface, that is represented by toe. Okay, toe equal to 60 megapascals. You need not represent it as toe max. Okay, toe itself is the maximum shear stress. Toe is equal to 60 megapascals. And also angle of twist is not to exceed 0.33 degrees. Angle of twist is given as 0.33 degrees. So two parameters given to calculate the diameter, stress and angle of twist. By using these two parameters, we can calculate the diameter, and out of those two, maximum diameter will be selected as required diameter. So per meter length means L equal to 1 meter. Angle of twist is not to exceed 0.33 degrees per meter length. So length is taken as 1 meter. Take G is equal to 80 GPa, 80 gigapascals. So 80 into 10 to the power of 9 newtons per meter square. This is the given data. Power P equal to 96 kilowatts. N is 180 RPM. D, you should calculate the diameter required. Maximum shear stress is 60 megapascals. Angle of twist 0.33 degrees. L equal to 1 meter, G equal to 80 into 10 to the power of 9 newtons per meter square. This is the given data in the example 4. Here, we are required to find the diameter, only diameter, one parameter in this problem. So first one, you should take as consideration as maximum shear stress. So diameter of the shaft by considering the maximum shear stress. If you consider the maximum shear stress, what is the diameter of the shaft? So let us take the power equation to know the torque. After calculating the torque, we can calculate the diameter by using the maximum shear stress. So power formula 2 pi nt by 60,000. Why I am using this power formula? The power is given in the problem, 96 kilowatts. Power transmitted by the shaft, 96 kilowatts. That's why I am using the power equation P equal to 2 pi nt by 60,000. It is in kilowatts. So P is 96 is equal to 2 pi into 180 is the speed, and torque we don't know the torque parameter, capital T divided by 60,000. So from this equation we can calculate the torque T equal to 60,000 into 96 by 2 pi into 180. That value of torque is 5092.95 Newton meter. 5092.95 Newton meter is the torque. By using this torque, we can calculate the diameter or the radius of the shaft by using torsion equation. We know that torsion equation is T by J equal to tau by R. That's the first two parameters from the torsion equation. T by J is equal to tau by R. From this, T is the 5092.95 divided by J is the polar moment of inertia. Formula is pi by 32 T power 4 is equal to tau value is 60 megapascals given in the problem. Maximum shear stress 60 into 10 to the power of 6 divided by radius of the shaft, or can be represented as diameter by 2, D by 2. From these two, D cube is equal to 232 is there, 2 is there, 216 and 1 D is cancelled, D cube remains here. D cube is equal to 16 goes into the numerator, 16 into 5092.95 divided by pi into 60 into 10 to the power of 6. This is the D cube value, 4.323 to 10 to the power of minus 4. Then D value, if you cube root this, then we will get the diameter 0.0756 meters. It is we will get the units for the diameter in meters. Otherwise, we can write in millimeters. Diameter is 75.6 mm. This is the diameter of the shaft required to transmit 60 megapascals, or to transmit power is, what is the power? To transmit 96 kilowatts power, diameter required is 75.6 mm. To develop the maximum shear stress is 60 into 10 to the power of 6 pascals or 60 megapascals. In the stress manam develop avali ante enta diameter use cheyalante 75.6 millimeter diameter rod or shaft use cheste inta stresses develop avutayi. ఇంతకంటే ఎక్కువ కూడా యూజ్ చేయొచ్చు, ఇంతకంటే ఎక్కువ యూజ్ చేసినా కూడా షియర్ స్ట్రెస్ అనేది 60 మెగాపాస్కల్స్ కంటే తక్కువ డెవలప్ అవుతుంది. దిస్ ఇస్ ద మాక్సిమం షియర్ స్ట్రెస్ that is a permissible stress in the shaft. The shear stress should not exceed 60 megapascals. సో ఇది ఎక్సీడ్ అవ్వకుండా ఉండాలి అంటే 75.6 millimeters diameter యూజ్ చేస్తే అది ఎక్సీడ్ అవ్వదు. ఓకే, నెక్స్ట్ angle of twist is also given in the problem. Angle of twist 0.33 degrees. So by using this angle of twist as consideration, we should find the diameter again. Diameter of the shaft by considering the angle of twist. So from the torsion equation again, g theta by h is equal to L equal to T by J. This is the another two parameter from the torsion equation. In the torsion equation, from this, G's value is 80 GPa, 18 to 10 to the power of 9. Theta is 0.33 given in degrees. If you convert into radians, pi by 180 multiplied by pi by 180, 0.33 into pi divided by 180 to length of the shaft is given as 1 meter per unit length. 1 meter is equal to torque T is equal to 5092.95 divided by J is the pi by 32 d power 4. From this d power 4 value, d is the only unknown parameter in this equation. D power 4 is equal to 1.125 into 10 to the power of minus 4. Okay, d is the 0.1029 meters or d equal to 102.9 mm. If you convert into the millimeters, we can write it as 102.9 mm. So in the first case, 75.6 mm is required diameter to avoid the exceeding of 60 megapascals, and second case 102.9 mm is required diameter for the angle of twist as consideration 0.33 degrees. So out of these two, 102.9 mm and 75.6 mm, we should take the maximum diameter, that is the maximum of these two. Higher of these two, we should use the diameter of the shaft to avoid the exceeding of 60 megapascals, the maximum shear stress, and angle of twist is 0.33 degrees. You don't exceed avakunda undali ante enter this equal diameter 102.9 mm. Therefore, the required diameter of the shaft is 102.9 mm, which satisfies both the cases. If you take the 102.9 mm as a required diameter, this satisfies both the cases. Both the cases means if you take the 102.9 mm, the maximum shear stress is not exceed 60 megapascals, and also the angle of twist is also not exceed 0.33 degrees. So you should take maximum value of these two as required diameter. Okay, this is the example 4 I explained to you, and example 5 you should take the again homework. It is a simple problem again. Example 5, I'll take it as homework. I will read out this problem and close this class, and in the next class I will explain the example 6 onwards. Okay, example 5 is a solid shaft of diameter 97.5 mm. It is the diameter capital D is 97.5 mm. Converted into meters, 0.0975 meters, transmits a torque of 6.36 kilonewton meter. So capital T value is 6.36 into 10 cube Newton meter. Calculate the maximum shear stress in the shaft. Toe value. What is the toe value? We should calculate by using torsion equation. T by J equal to toe by R. That using that equation, we can calculate the maximum shear stress in the shaft. The answer is 34.94 megapascals. It is in megapascal, 34.94 toe value. So solve this problem by using the torsion equation and compare your answer with this given answer. Okay, students, let us close at this point. I will explain the next in the next class, example 6 onwards. Okay, students, bye. Have a nice day.